which has 6 companies, and the theme with all of them is vibration. So the whole company, the whole group, vibration and sound is at the core of what we do. So DJB is sensors primarily. ProSig above that is noise and vibration measurement, so the data acquisition and display of noise and vibration parameters. 2 companies then, Semia and Helitune, are involved in helicopter vibration management and analysis, and Baran Instruments is involved in vibration condition monitoring in the energy sector. But today I'm largely focusing on DJB, the sensor company. And some very brief background. So 44 years it's been founded. We used to be called DJ Birchall after the founder, Don Birchall. He left the company 15 years ago, and we're located in the UK, around about 100 kilometres north of London, near Cambridge. We were acquired by the CNPG company 2 years ago, and we're one of the few European manufacturers of test and measurement accelerometers. And as you're aware, we're represented in Spain and Portugal by TSI. And 2 slides on the company. So we're unique, we think, in manufacturing most of our components in-house. So the accelerometer bodies, the blocks, any insulators, the tungsten masses, and the brass for the connectors, we make all those. And the key thing with that is we don't have a complex supply chain. So we very rarely suffer from extended delivery times, because the majority of manufacture of the items needed for an accelerometer, we actually make ourselves. And we have a full in-house calibration facility for both accelerometers and impact hammers. And some of our customers, we're a smaller company than some of the big accelerometer companies, but when we look at our customer base, we certainly have some pretty top customers out there that use DJB. So just with some of those in the automotive sector, Ford, Seat, Audi, Volkswagen, and Stellantis Group are some of the automotive ones. Aerospace, BAE Systems for a lot of their wind tunnel work. RAL Space, which is one of the biggest space test facilities in Europe. Airbus, both the space and the commercial airliner side, and Rolls-Royce Aero Engines. Petrochemical and some energy, so EDF, Uniper, RWE are key customers. And we do some work with Formula One companies as well. So you can see top right there, Red Bull and also McLaren. I'll come on to a couple of those customers a bit later and as to why they've used DJB. So looking at our range of accelerometers and the selection, so that's a lot of the range there. And if I just activate my cursor, which so we make what we think is one of the world's smallest accelerometers, which is just where my arrow is pointing here, which is a tiny 0.19 grams accelerometer, used predominantly when you're trying to do modal type testing on very small structures where you don't want to load the structure with anything that would affect its response. Then we have a range of normal sort of size ones, so moving up from that's the ultra miniature to some miniature ones, some general purpose type ones, some triaxial accelerometers over here. This one is an ultra high temperature sensor, which is water cooled and goes to 900 degrees, which I will come on to a bit later, and industrial type sensor here. So a fairly broad range of sensors that cover the majority of the test market. And we use a technique called conic shear. So I'm sure everybody's aware the 2 main types of shear are compression and the shear. So conic shear, you can see actually operates with a conical shaped. So you have the ceramic here and then the mass, and it's in a cone shape. We had a patent on that when it first came out, which patents expire after a while, so it has now expired. But we're the only people to use this, and the real benefits of this is you get virtual isolation of the sensing element from mounting induced strain. if you mount an accelerometer using a stud and you over tighten it with normal accelerometers using the compression or shear, you can induce an error simply by how much you tighten the base, because you're putting a preload onto it. Conic shear is virtually immune from that. Minimal cross-axis error. So cross-axis is the error that's induced by sideways vibration, if that's the right word to use, when you really want to be measuring only the acceleration in the vertical direction. If there's any horizontal vibration, that should be rejected, and conic shear is exceptionally good at doing that. Has a high resonant frequency, which is always important in accelerometer, particularly during shock testing, and have very, very rugged design. They do last a long time. And when specifying an accelerometer, it looks as if an accelerometer is fairly simple to specify when one's needed, but there are a number of things that need to be taken into account. So the mass is the first one. Generally, you want as low as possible. However, there is no point putting an expensive, tiny accelerometer onto something like a gas turbine, because it just is irrelevant to do that and not appropriate. So mass loading becomes more of a consideration when you're testing smaller mass structures. Single or triaxial, which directions do you want to be measuring in? What's the sensitivity you need? The normal ones are either 110 or 100 millivolts per G. And that's highly dependent on the maximum acceleration level you're likely to see. What's the frequency response? What temperature range do you need? Because that dictates whether you have IEP or charge. Where do you want the connector? So access to the connector, is that top or on the side, which I've got an example later. How are you going to mount it? Glue, stud, wax, or isolation? What cable type do you need? Do you need any special calibration for it? Most accelerometers are calibrated between 10 hertz and 8 kilohertz. Do you need extended calibration on that? What are you connected to? And do you need isolated or non-isolated base or case, of which I have an example later. And the various mounting techniques, I will go through this quite quickly. There's a number of ways you can mount the accelerometer. These are the classic ones. The optimum one is a tapped hole or a stud, because you get superb mechanical coupling between the test specimen and the accelerometer. However, you may not necessarily want to drill a hole and put a stud into your test specimen. So, but that's by far the superior one. Then we come down. The next one is super glue. You don't need to drill a hole. Get good high frequency coupling. Double-sided tape. Again, you can get frequency response issues at the higher temperature, but super glue and tape do not need any modification of your test structure. A clip is one method of doing it, where you want to move the accelerometer around. You can just secure the clip in one direction. Petrowax, again, very quick, but you can only use up to ambient temperature, and then a magnetic base. Which is often used in industrial applications where you've got a ferrous material. But the key message is that there are advantages and disadvantages in all of those, but we can supply a sensor that really uses all of these different techniques. We have what we think is unique in the world. Actually, let me just go back a slide, because I forgot to point out. So the ultra miniature temperature we do, which we believe is the world's smallest, you can see in the bottom right here next to a pencil nib. So that really is very tiny, 0.19 grams, used in modal type applications. The water-cooled sensor, so another area where DJB are unique. You can generally go to about 450 to 550 degrees centigrade with a normal crystal type accelerometer. Then you can't really go above that without damage. For some applications, though, mainly automotive and some gas turbine test applications where you're on the very hot part, we produce a water-cooled version of an accelerometer which can measure up to 900 degrees. Which is about 250 degrees higher than virtually anything else on the market. And the classic application, automotive, as I mentioned, is is exhaust manifold and turbocharger type testing. Here you can see one mounted on an exhaust manifold. It's water cooled, so you need to supply it with a small water pump, something like a windscreen washer pump, and maintain the flow whilst the sensor is on the hot surface. There's also two versions of this. You can see one here with a flat base and one which has got an extended base. That's to allow customers to mill a radius onto there. If you want to fit this sensor onto a curved manifold where you need to get the coupling good to the surface, then a flat surface naturally won't give you good coupling onto something like a tube. So the radius of the test item can be milled onto here, or the profile of it can be milled onto here. For the vibration engineer or structural engineer, we also offer a range of instrumented impact hammers, ones which are really quite small, with the hammer mass being 24 grams, right up to one down the bottom here with a hammer mass of 1,300 grams if you're testing things in the power industry or energy industry where you're trying to impact a force into quite a large structure. Small bridges as well would use that. Okay, so just to talk briefly about three of our customers and applications. So this is a space test application. This is one of Europe's largest satellite testing facilities. They can test a satellite up to 7 tons. The facility allows vibration, acoustic, temperature, ultraviolet, shock and vacuum facilities. So a satellite can virtually be put through the whole launch sequence in terms of the shock and the vibration, the temperature, the acoustic, etc., that it would experience during launch. And then with the vacuum and UV, it can also test it as if it were in space. We supplied about 30 IEP sensors for this, for shock testing. And our sister company, ProSig, also supplied a multi-channel data acquisition. So the middle photograph actually shows their shock test machine. So the satellite, or this wouldn't necessarily be a large satellite. So a satellite component or a small satellite is bolted on this face of the plate. And then we have a pneumatic ram system where this ram is fired at the back of the plate. And just here, where you can see this red mark here, in order to modify the shock pulse to either make it a very sharp rise time or less, they would put a material between here, which can be some sort of plastic, aluminium, or even steel if they want a really sharp rise time. So this is a brand new facility. It's now in operation, and yeah, we're very proud that we've supplied the sensors for the shock testing, and also our sister company has provided the data acquisition system, which are, from memory, is 512 channels, which is connected to a number of different sensors on the satellite. So as I mentioned, 30 of the A120, so we've supplied these two versions at the front. So they wanted a number which was side entry for the cable and a number which were top entry for the cable, because sometimes on the structure you can't necessarily get the cable out in the optimum direction. So it gives them a choice of where the cable exits. We also supplied the low outgassing cables, which I'm sure everybody's aware, when a satellite is being tested in ultra clean conditions and a vacuum, they can't have any situation where the vacuum causes any sort of gases or substances to leak out of the cables. So that was 30 sensors, 40 cables, and we were chosen for the high resonant frequency of our sensor, which is quite important when you're doing shock testing, and also our delivery time. As I mentioned earlier, because we're in control of most of our manufacturing and don't have complex supply chains, we can normally deliver quite fast when we have to. And on the ProSig side, so this was a 500 channel high-speed data acquisition system, which is just here. So this is the high-speed data acquisition system, which they wheel from room to room to do various testing, whether it's on the shakers as here, or whether it's in the shock test facility. The channels were a combination of voltage, also strain gauges and thermocouples. And a key element in the decision was our channel synchronization, where all 512 channels always had to be synchronized together within just one data point. So that's a aerospace type application. This one's Stellantis. So electric vehicles, obviously up and coming. The battery packs in those, of which you can see a generic battery pack there in the middle, they have to undergo some quite stringent qualification and production testing, mainly because they're lithium. Lithium can have a combustion condition under certain conditions, and obviously the voltages are very high in electric vehicles as well. So an EV battery has got multiple cells and they're assembled into one unit, and then the manufacturing criticality to make sure there is no looseness in the structure, no electrical leakage in the structure, and no movement between the cells. It's quite a complex sequence of testing for both electrically and for vibration. So what happens to the cell in a crash, etc. So we supplied around 500 of both these two devices on the right here. So the AT10 is the AT10 at the top here is a small, it's about 8 millimeters by 8 millimeters triaxial accelerometer. And then the AT18, which is an ultra miniature, that's a triaxial sensor. You can just see on the photograph the X, Y, and Z markings on it. And you can see for scale that's next to a paperclip. But the key thing we had to do with this was to make them base isolated. So given the voltages and potential currents that can flow, then the whole testing system and the sensors had to be all isolated to prevent any chance of any short circuits occurring during testing, particularly when you have these particularly high voltages and the ability for high currents to flow. And then the final one, this is a petrochem plant, which was a really interesting study of the problem they had. So they had 3 of these, so that's just a generic picture of the plant. So they had these ductings over here, which have got 2 motors at the bottom with fans, and then they merge into one. This is around 20 meters high, 25 meters high, because it goes up to floor 5. And they had an issue with vibration. And one of the first things they did, as we know with vibration, you can change the resonant frequency of something if you stiffen it. And they tried to stiffen the whole thing by putting extra support brackets along part of the ducting. So they were trying to raise the resonant frequency above what the problem was, but that didn't cure it. So they decided to embark on some testing. So they use AT14 down here, the triaxial accelerometer, which is a larger version. It doesn't need to be a miniature version to be put on large ducting. And first of all, they did quite a complex hammer test. So that's up here, the results of the hammer test, where they had the accelerometers permanently fitted, and they tapped the structure at various places with the hammer to first try to characterize what the resonant frequencies of the structure was. Then they did various they ran the fans at various speeds to see if they can introduce some resonance, but that didn't happen. So that the fans were run with no load. And then they ran the fans with various load and found it was a problem called rotating stall, where it happens when there is insufficient airflow coming into the back of the fan to be accelerated by the fan as it comes out the other side. If you have insufficient airflow, then you have this issue called rotating stall, where the fan blades, the impellers start to vibrate, and that then was causing vibration to propagate through the structure. And so they carried out with the manufacturer some intake modifications, which was changing 2 things. They increased the size of the intake flow, but they also changed part of there's an S ducting type arrangement at the bottom, and they changed the ducting to make sure the air was, when it came in, was not coming in at a slight angle, which was happening as well, which was causing part of the rotating stall. So that's 3 typical applications. I notice my time is up. So I will say thank you for being here and listening, and if anybody has any questions.
Muchas gracias, Tim. Y Jorge, la verdad es que habéis visto en esta presentación, bueno, DJB es un fabricante de productos que tienen mucha peculiaridad en temas de, por ejemplo, bueno, medición de alta temperatura, miniaturización especialmente para bancos de prueba en el sector electrónico y aeroespacial. Y bueno, Jorge os ha explicado un poco también cuál es nuestra gama de servicios que damos TSI, que puede complementar perfectamente el suministro de equipos para medición de vibraciones. Entonces, bueno, pues tenemos aproximadamente unos 10-15 minutos para responder a vuestras preguntas.